Here's a question that might sound like it belongs on a math exam for kindergartners. Take two numbers you know very well, e, roughly 2.71828, and pi, roughly 3.14159, and add them together. You get something around 5.859. Now tell me, is that number rational? Can it be written as some fraction, p over q, where both p and q are whole numbers? You'd think this would be easy. I mean, we've known about pi for thousands of years, we've known about e for centuries, we can compute each of them to trillions of digits. And yet, right now, no living mathematician can tell you whether e plus pi is rational or irrational. Nobody, not a single person on Earth. We can detect gravitational waves from black holes colliding a billion light years away, but we cannot answer what feels like a grade school question about two of the most fundamental numbers in mathematics. And what I want to show you today is that this isn't just some quirky gap in our knowledge, it reveals something genuinely unsettling about the limits of what mathematical proof can reach. But before we get to the hard stuff, let's make sure we're all standing on the same ground. What does it actually mean for a number to be irrational, or better yet, transcendental? Think of all the numbers you can build using whole numbers and basic algebra. Start with the integers, 0, 1, -7, whatever. Take ratios of those, and you get the rationals. 2/3, -11/4, that whole number line's worth of fractions. Now go further. Consider all the roots of polynomial equations with integer coefficients, things like the square root of 2, which solves x squared equals 2, or the golden ratio, which solves x squared minus x minus 1 equals 0. These are the algebraic numbers. They form this enormous family, actually countably infinite, so in a precise sense, listable, of numbers that are reachable by algebra. And then there's everything else. The numbers that are not the root of any polynomial with integer coefficients. These are the transcendental numbers. And here's the wild thing. Almost all real numbers are transcendental. If you could somehow throw a dart at the number line with perfect precision, the probability of hitting an algebraic number is exactly 0. Transcendentals are the overwhelming majority, the ocean, while algebraic numbers are a scattering of tiny islands. Pi is transcendental. Lindemann proved that in 1882, and in doing so settled the ancient Greek problem of squaring the circle. It can't be done. E is transcendental too. Hermite showed that about 9 years earlier. So individually we understand these numbers quite well. We know exactly where they sit in this classification landscape. Both are transcendental, which is a very strong statement. It means no polynomial with integer coefficients, no matter how high the degree, no matter how cleverly you choose the coefficients, will ever have e or pi as a root. So why can't we say the same thing about e plus pi? This is where things get genuinely surprising. You might think, well, if two numbers are both transcendental, surely their sum is also transcendental, or at least irrational. But that's just not true. Take pi and the number negative pi, both transcendental. Their sum is 0, which is as far from transcendental as you can get. It's an integer. Or take e and the number 1 minus e. That second number is also transcendental, but their sum is just 1. So transcendence is not preserved under addition. The transcendental numbers don't form a nice closed club. And here's where I think the real shock lies. We do have powerful theorems about e and pi individually. The crown jewel is the Lindemann-Weierstrass theorem, Lindemann in 1882, generalized by Weierstrass in 1885. Roughly, it says that if you take algebraic numbers that are linearly independent over the rationals, say alpha 1 through alpha n, and you raise e to each of those powers, then the resulting exponentials are algebraically independent over the rationals. That's an incredibly strong statement. It's what lets you prove e is transcendental. Just set alpha equal to 1, which is algebraic, and you get that e to the 1 is transcendental. It's what proves pi is transcendental too, via a direct application using Euler's identity. If pi were algebraic, then I times pi would be algebraic, and Lindemann-Weierstrass would force e to the I pi to be transcendental. But we know e to the I pi equals -1, which is decidedly not transcendental. Contradiction. But notice the structure of what Lindemann-Weierstrass actually talks about. It tells you about e raised to algebraic powers. It tells you about relationships among exponentials. What it doesn't tell you, and this is the critical gap, is anything about what happens when you take a number like e and just add it to pi. That operation, plain addition of two specific transcendental constants, is completely outside the theorem's reach. It's not that the proof technique barely misses, it's that the theorem is making statements about a fundamentally different kind of relationship than the one we're asking about. Now you might ask, well, is there some other theorem, some other tool that could handle this? And the answer is, sort of, but it's unproven. In the early 1960s, a mathematician named Schanuel proposed a conjecture, first recorded publicly by Serge Lang in 1966, that, if true, would essentially blow the whole problem wide open. Schanuel's conjecture says this: if you take any n complex numbers that are linearly independent over the rationals, then among those n numbers and their exponentials, that's 2n values total, the transcendence degree of the field they generate over the rationals is at least n. In plainer language, at least n of those 2n values are algebraically independent over the rationals. That might sound dry, but the consequences are staggering. If Schanuel's conjecture is true, you can prove that e plus pi is transcendental. You can prove e times pi is transcendental. You can prove that e to the power of e is transcendental. Essentially, every obvious open question about the arithmetic of fundamental constants would fall like dominoes. It's a single statement that would resolve dozens, maybe hundreds of open problems at once. And the maddening thing? Almost everyone believes it's true. It's consistent with every transcendence result we've ever established. But belief is not proof, and Schanuel's conjecture has resisted all attempts at a proof for over 60 years. The frustration here runs deeper than just one unsolved problem. It points to something structural about how our proof techniques work. Most of what we can prove about transcendence goes through the Lindemann-Weierstrass theorem or its extensions, and those tools are, at their core, about the exponential function. They leverage the very specific algebraic properties of e to the x, its differential equation, its role in complex analysis, its connection to the integers via things like Euler's formula. But when you just add two numbers together, even two numbers you understand individually, you're stepping outside that machinery. Addition is in some sense too simple an operation for our most powerful tools to get a grip on. The astute among you might notice an irony here. Addition is the first operation we learn. It's the most basic thing you can do with numbers, and yet in the landscape of transcendence theory, it's an operation we can barely say anything about. There is one thing we can prove, and it's worth holding on to because it's a beautiful partial result. We know that at least one of e plus pi and e times pi is irrational. Here's why. Consider the polynomial whose roots are e and pi. That's x squared minus the quantity e plus pi times x plus e times pi. The coefficients of this polynomial are exactly e plus pi and e times pi. Now, if both of those were rational, then this polynomial would have rational coefficients, which would make both e and pi algebraic, roots of a degree 2 polynomial with rational coefficients. But we know they're transcendental, contradiction. So at least one of e plus pi and e times pi must be irrational, at least one. But which one? Maybe both? We genuinely cannot say. So think back to where we started. Two numbers, e and pi, each understood to extraordinary precision, each proven to be transcendental by theorems that rank among the most beautiful in all of mathematics. And yet the moment you do the simplest possible thing, the thing a 5-year-old could do, just add them together, you've stepped into a void where our deepest tools go silent. It's not that mathematicians haven't tried hard enough. It's that the architecture of proof itself seems to have a blind spot right here, right at the intersection of the exponential world and the arithmetic one. And maybe that's the thing to sit with. Mathematics isn't just the collection of truths we've proven. It's also the shape of the darkness at the boundary, the questions so simple to state that you could fit them on a post-it note, yet so resistant to proof that they might outlast all of us. E plus pi is roughly 5.859874. That much we know. What we don't know is what kind of number that is. And the fact that we can't tell, that might be the most revealing thing about mathematics of all.